We're ready to start. Welcome everyone to this second lecture of the TCP-IP course. The program today will finish a few little things of last week, and then we'll talk about the IP layer, at least our first catch at it. Tomorrow, the first test. The program is everything including what we see today. And then lab 1, which will be a 2-week lab. The last thing I want to do about the architecture is to put things together and recall something that you have hopefully discovered already in lab 0. So we'll do an analysis of what happens when this computer sends a packet to this device here. What is special here is that we have 2 local area networks, the Wi-Fi and the Ethernet, that are interconnected by a router. Here is the layered diagram that corresponds to this scenario. Here I'm showing Elaine's device, the computer, the web server, and the router in between. The first thing you observe is that, in principle, the transport layer is absent from the intermediate point. That's first thing to remember. The transport layer is end-to-end. So TCP is not involved in the router when we send the data. The application, of course, is not. If the application would be involved, we would be doing store and forward like in the old days, but we don't want to do that. We do packet switching. Now let's go through the sequence of events that occur when the web server sends some data to the web client. This is a sequence of events that you will implement in lab 3 in Python programs here. So let's look at what happens from the top to all layers. So the application program uses sockets or higher level abstractions. We'll talk about some of them later. And does, for example, a send into S2. S2 is the name of the socket. That's a data structure that's offered by the transport layer implementation to send the data. And data block is a block of data. This block of data, in this case, is too large to fit in one IP packet. So it is segmented into 5 smaller blocks that fit. It's segmented by TCP, by the transport layer protocol. And then those 5 blocks each are put in one IP packet. The green stuff is the IP header. Now the IP packet has to be transported to the destination, but first to the router. And since this is an Ethernet local area network, this is done using the Ethernet format, which is essentially shown by adding here a red overhead, which is the Ethernet header. The packets, the 5 packets, are transmitted over Ethernet to the router. Then the router receives them. It receives them because it analyzes the MAC destination address. It knows it's for me. And it removes the MAC header. And then it has IP packets. Each of those IP packets is analyzed. Essentially, the IP header only is analyzed. The IP header contains, in particular, the IP destination address that will tell the router where to go. It has to go to the wireless LAN. So it will send the packets again, but now through the wireless LAN, which means it will put a wireless LAN, a Wi-Fi header, which is more or less the same as an Ethernet header, but has a few different fields that are specific of wireless. We'll talk about them in 1 week. Then the packets, here packet 1, 2, 3, but also the others will follow, are sent over the Ethernet over the wireless LAN to the final destination that will then remove the LAN header and receive the 5 segments. Question?
When you do the red and orange, is it just because one is wireless, the other one is wired, or is it also because in the first packet the MAC address is actually the MAC of the router? So the MAC address that it sends it to is the next hop, and then when the router receives it, it replaces that with the MAC of the destination.
So what is the question?
My question is the red just because it's different kind of transmission, or is it because actually the address that's encapsulated in the header is actually different?
So why did I pick red and orange?
Well, not why this color, but
yeah,
are they different because of the mode of transmission, or are they different because the address is different?
No, they are different because they are not the same LANs. If they would be both Ethernet, everything would be exactly the same.
So the MAC address that's encapsulated in
the MAC address is, so when you send a packet here, you send it to the router over Ethernet. So the MAC address has to be the MAC address of the router. Otherwise, it won't work. Right? If you send the MAC address of this guy, it's not on the Ethernet LAN, so it won't work. Correct. And then eventually, the application would read the block. Now, be careful, this diagram, you can't show everything in one diagram, so it might be misleading. Here, the 5 packets are transmitted together, but this is not how things happen in reality, except if the network is really, really very, very fast. Probably they are transmitted one after the other, and it's quite possible that packets 1, 2, 3 have arrived while packets 4 and 5 are still being transmitted here. So everything here can happen in any order. In particular, as I mentioned already, it may be that packet 1, 2, 3, 4, 5 don't arrive in exactly the same order, in which case TCP will take care of waiting until everything has arrived in the correct order so that the application doesn't see the misordering. TCP guarantees in-sequence delivery of data. Some terminology, which is perhaps the only non-completely trivial thing here. A packet done by TCP is called a segment, done by IP is called a packet, and by the MAC layer, a frame. So the word segment is very stable, and everybody will use the same. The word frames, as I mentioned, sometimes are used by, we use packets as well. If you want to be formal, the correct names are given by this diagram. This is illustrating the 2 interfaces that exist when we do networking stuff. There is an interface that is between entities that are at the same level. This is when TCP speaks to TCP, or when an IP host sends a packet to an IP router, they both speak IP in that case. So what governs the interaction between 2 things at the same layer is called the protocol. That's the definition of a protocol. So IP is a protocol, TCP is a protocol, so the TCP protocol says what are the fields that you find in a TCP header, how do you number the packets so that you can retransmit them, everything is defined here. There is an interface between layers of the same machine, those are called service interfaces. And the service interface is not necessarily the same as the protocol. For example, if this is TCP, the service interface is the socket layer that we will do in Lab 3. It says how I can speak to the operating system to retrieve data that have been sent to me using TCP, or how can I send data to someone using TCP. That's the service interface. The elements of information that are passed across a service interface are called SDU, service data units, and the elements of information that are passed across a protocol interface are called the PDUs, protocol data units. So sometimes you will say that an IP packet is an IP PDU, and a TCP segment is a TCP PDU. In contrast, the TCP SDU is a byte, because TCP offers a byte-by-byte service. This is only terminology. Once you know that, you can use the correct words, and more importantly, understand what you read. But that doesn't help us in understanding how things work. Some other element of terminologies that you've already been confronted with and you will immediately discover in Lab 1 and 2 are words like switches, routers, and bridges. A router is, by definition, an intermediate system of the layer 3, of the network layer. It is something that analyzes IP headers and forwards the packet somewhere else. A bridge is the same, but at the MAC layer. It analyzes the MAC headers and forwards them to the destination. Sometimes you need a bridge in a LAN. That's typically how Ethernet works today. Sometimes you don't necessarily need one. For example, if you use Wi-Fi in ad hoc mode, for example, with an iPhone and AirDrop, you can send a packet directly from one machine to the other over the Wi-Fi protocol without a bridge. And another terminology that is more misleading is a switch. So switch most of the time means exactly the same as a bridge. But sometimes you will hear also layer 3 switch. Switch historically meant something that is forwarding packets and does it very fast and in hardware. So it's a marketing name, if you want. Originally, the network layer is implemented in software, and everything below is implemented in hardware. That's a boundary we tend to continue to find also today. So most systems are organized in this way. The Ethernet adapter, the Ethernet is done on the Ethernet adapter, which is a hardware you buy from Intel or some other companies. The network layer is the operating system, so it's Microsoft or Apple that does it for you. So this is typically software, and this is typically hardware. But this is not necessarily so. The words router and bridge have to do with the architecture, with the TCP-IP architecture, with the function. A router forwards packet by analyzing IP headers. You typically did that in software, but now most modern routers also do it in hardware because they are very important, it's a commodity, and this makes things faster and cheaper. Bridges can be done in software, but most of the time they're done in hardware. We will see software bridges in the virtual machines environment that we will use. So those software bridges are sometimes called switch. Layer 2 switch means exactly bridge. Layer 3 switch means almost exactly router. The difference typically is that a router does packet forwarding based on IP header. That's a definition. In order to do the packet forwarding, it needs to know where to send the packet. It needs to have a routing table. We'll talk about it in a few minutes. And this routing table is normally acquired via participation in a routing protocol. That will be the topic of several weeks and Lab 4 and Lab 6. A Layer 3 switch typically does not participate in a routing protocol, but gets the routing information directly from network management. But those are all shaky differences. So for me, I prefer to equate everything. Layer 3 switch is a lazy term for a router. Layer 2 switch is a bridge. Last way of seeing the things we've been discussing in this module is to see how things fit together, which is what you do when you look at packet capture traces. When we send a packet over the Wi-Fi or Ethernet, we have a packet that has, or frame, that has a MAC header that contains, for example, the destination MAC address, plus other things that Wi-Fi needs, for example, to avoid collisions between multiple senders. Inside the payload, so the word for the useful part of a packet is the payload, but the useful part of a MAC packet is typically an IP packet, IPv4 or IPv6. Practically, those are the only packets that today we transport in the MAC layer. Not always, but practically always. Then the payload itself is not exactly the useful part because an IP packet also has a header that is containing, for example, the IP destination address. Then if we are using TCP, we will have the TCP header and perhaps here the TCP payload. Usually we also have another kind of header. What could it be inside TCP? No, that would be weird to transport UDP inside TCP. You can, everything is possible. This is software, but that's a bit weird, yeah? HTTP, exactly, HTTP, the application layer protocol. And between HTTP and TCP, what do you sometimes find, or very often find? SSL, or TLS, or the security layer that does encryption. So you can have all the application layers and sublayers that will also encapsulate this. And when you do packet capture display, you will see all those things. When you see such things, for example, here I'm showing the IP header. In the IP header, I see a source address, which is an EPFL IP address. I also see a name, lrcpc3.epfl.ch. Where does this name come from? Is it in the packet? From? From ARP? No. No. From DNS. Yeah. But was the name in the packet? No. It was added by whom? Yeah, by the software that does the pretty printing. So when you do the packet capture, there is no name in it. There is just an IP address. The IP address is in the packet in the form of bits and bytes. The software analyzes the bits, translates it into a number, and then goes to the DNS to do a reverse DNS query, asking what is the name that corresponds to the IP address. DNS is used normally for the reverse. What is the IP address that corresponds to the name? You can do also reverse query, in which case you will get those things. Similarly, telnet is not written in this, but the port number is 23, and it is well known and hard coded in the software, probably, that 23 corresponds to telnet. Last question on this module. I'll let you discover and provide me your answer through speak up using this room number if it doesn't come automatically to your device. I close in 5 seconds. And the majority is right. The correct answer is A. The destination MAC address, in fact, you asked the question a few minutes ago, the destination MAC address is the MAC address of the router because the web server has to use Ethernet to reach the router, and the only way to reach the router is to put the MAC address of the router. The destination IP address, well, has to be the IP address of Elaine. In fact, the network layer is global. The network layer addresses are meant to be global, so it's like in a postcard, you put the final destination address here, so the correct answer is A. Right? If you send to the IP address of the router, that means you're talking to the router, which normally you don't do, except if you're managing your router. For example, if at home you have an ADSL modem that is also a router, and you want to do something with it, perhaps after this course, you want to play with the NAT table, then you can go into the router with an HTTP interface to configure it. But if you do that, the packet will stay at the router. The IP destination address is the final address. In principle, of course, everything can be contorted, as we will see later, but it's better first to stay with the principles. Voilà, that's the end of this first introductory module. Any questions? Then we'll go through the details of the IP layer itself. Those details are fairly easy, but what is important is to know what are the leading ideas. And then beyond the leading ideas and the easy part, there's lots of more cumbersome details. In line with the philosophy of this course, we'll go through some of those details, and hopefully it will not be too painful. So the IP layer is the layer that unites all the computers and devices in the world. I mean, when it was originally done, it was for computers, but today it's envisioned to be able also to interconnect an intelligent thermostat in your house to an application server at a company that's managing the energy of your house, for example. For this, the network layer of the internet, IP, follows two principles. There were other network layers that were developed, and they had slightly different principles. But it looks like those principles are the ones that survived the competition between networks. The first principle is that the addresses are structured and the routers, the intermediate systems, do longest prefix match. So every interface has an IP address. If you have several interfaces, for example, your computer might have Wi-Fi and Ethernet, in which case you will have a different IP address for each of those. And the IP address is structured to reflect where the system is in the world. We've seen that. There is a subnet that identifies that you're at EPFL and where at EPFL you are. As we've seen, every packet contains the IP address of destination, and then all the systems, including the hosts and the routers. One of the principles of that is that we find practically everywhere in Unix. I mean, all this is done by people who work similarly to Unix developers. So one of the ideas is that there's no difference between a host and a router. except if you really need to. For example, a router runs a routing protocol, a host does not. But other than that, the IP is the same in a host or a router. When I say the IP, it means the IP layer. Very often when people say the IP, they mean the IP address, right? Something I hate to remove the word address, but okay. So the principle is that every device that does IP has a routing table. It is sometimes called a forwarding table, sometimes a routing table. They mean the same. And you perform longest prefix match. What does longest prefix match mean? It means, for example, here I'm showing a very stylized version of IP routing table. So A has an address A.H1. Destination has an address B.C.H2. Those are more like IPv6 addresses where there's lots of space and there is some space that truly identifies the host. And if we focus at router R2, then router R2 had to go through this table. That's a typical router table. It's not the way we see it is, we'll see in a few minutes how it is. Here in this stylized version, I wrote A.star. That means any address that starts with A and has anything after that matches this entry. And we have two entries that start with B, B.D.star and B.star. When this packet came, the destination is B.C.H2. It matches the third line only. So we go to the third line, which says the interface output is number 3. So this packet goes here. The forwarding table has other information, like you will quickly discover. There is the interface number, also called port number, but it has other things, like typically what is the IP address of the next hop. If, in contrast, we have a packet to send to this machine here with the address B.D.H2, then this router has two matching entries, the second line and the third line. And longest prefix match simply says we take the one that matches with the longest prefix, which is B.D here. So it will go here and not there. That is how internet address analysis is organized. And so why is that powerful and useful? Any idea? Yes? Yes, we can do hierarchy. So here, for example, we say that if the whole of B is here, then I simply need to put one exception, which is here for something a bit more specific here. So if you are, for example, in a large network, but you're just close to the exit or the entrance to this network, then you can have a few entries for the special cases, like B.D, and one regular entry for the rest. In particular, one entry that we will often find is the 0 entry, or the empty, there is nothing, which means everything matches. This means that's the default route. If you're a device and you want to say everything that you don't know where to send, you send to a default route, to typically, this is what your host does, it sends to the next hop router. And longest prefix match means you can have this entry, and if you want more specialized entry, you add them, but you need only to add the exceptions, not having to describe all possible cases. Second principle that we have seen already, at least in a form, is that IP is aware of local area networks. And as I mentioned already, it's why there is the Internet protocol, not the net. It's not NP, it's IP. So IP views the world as a connection of local area networks. And the rules are, if two devices are inside the same local area network, they should find a way to communicate directly. IP should not bother about that. In particular, routers should not be involved. And if two hosts or two machines are not in the same local area network, they have to use routers. So for example, here, communication from B to E should not go through the router, and communication from W to E has to go through a router. A LAN seen from the IP viewpoint is called a subnet. And we have seen how routers, how systems decide whether they are on the same subnet or not. Okay. But before that, a little question here. We observe a packet from W to P at this observation point number 1. Which IP destination address do we see at this observation point? I close in 5 seconds. And the correct answer is the majority. Do you see the results on your devices? Yes. Okay. So the majority says A, with a large minority saying C. And this is the interest of this question. The correct answer is A. So there is, we saw that a minute ago, the principle of IP is we don't use routers to go in between, but there is always an IP layer. So if a TCP-IP host speaks to another TCP-IP host, there is always an IP layer. So there is always an IP destination address, even if W talks to P. If you use TCP-IP, there must be an IP destination address, but it's not used. W will know that it has to send it to the MAC address of P, and therefore P will receive it directly. So it's not used for forwarding because there's no router in the path. Of course, if it would be the IP address of the Ethernet concentrator, that would be a problem like we saw a few minutes ago. So that's pretty much it for the IP protocol, except for a few details about addresses that we will discuss abundantly now. In particular, there are 2 IP versions, as we saw, IPv4 and IPv6. And those addresses are different and allocated in different ways. And given the importance of those IP addresses, we will need to be very comfortable with them. So this is what we will discuss now. The IPv4 addresses are short, therefore they are simple. As we discussed last week, they are 32 bits, therefore not enough to cover the whole world when everybody will have 4 or 5 addresses. They are typically written in this form, which is dotted decimal. One integer represents 8 bits, which means a number between 0 and 255. And here are alternative representations. So those are 3 ways of representing those same 2 addresses. The binary one is the one that the computer sees. For us, it's practically impossible to work with bits. Therefore, we very often, if we want to manipulate bits, we manipulate hexadecimal digits. See here in this slide, the X means it's hexadecimal, the B means it's binary. And 80, for example, corresponds to 128, which you see here, because 8 corresponds to this block of 4 bits, and 0 is this one. So the mapping from hexa to binary is very convenient, because one hexadigit is exactly 4 bits, whereas with the integer, with the decimal integers, it's a bit less tricky. Not tricky, but not less obvious here. I think we went through all this. Routing tables, as I mentioned, are present in routers, also in hosts. So here I'm showing the routing table in this blue router in the middle. Here is how it looks like, not a dot star like I said a minute ago, but it has prefixes. For example, it has here this prefix, which is exactly a subnet prefix, 128.178.29, which corresponds to one of the subnets to which it is attached, which is, I don't know, one of the subnets to which it is attached. And it has also, and the /24 means 24 bits of this prefix, 24 bits of this string are relevant, which in this case is exactly all the strings. 128.178/16 means the prefix that starts with those 16 bits. And then we have the 0./0. So here it means that this router has a specific route for one of the subnets that's connected to it. Then it has a different route for the rest of EPFL and a default route for the rest of the world. So this is something that leads to the outside. This is something that leads to the backbone of EPFL. And this is something that leads to a specific subnet that is not reachable via the backbone directly, or the optimal path doesn't go through the backbone. We saw the concept of subnet and subnet mask, so here it's a bit different. Here, one prefix corresponds to exactly one subnet, but here we see prefixes that are smaller than a subnet. So this prefix here means all the EPFL subnets. Right? So subnetting is just one specific way of defining a prefix that is used by hosts to know in which local area network they are. But more generally, we can use this prefix notation, which is done here. There is a whole set of special cases. We have seen some of them already. Those addresses, 192, 168, 10, are so-called private addresses. They are addresses that we use all the time. Private means you can do with them whatever you want, but you should not expect to be connected to the internet. So you build your own private network with those addresses. They don't belong to anybody. Everybody can use them. 128, 178 belongs to EPFL, so it's not legal for another company somewhere in the world to build a private network and use the 128, 178 address. I'm not sure anything serious would happen if their network is really private and not connected to the internet. But in principle, those addresses belong to some entity that has received them. Those ones don't belong to everybody. As a counterpart, they cannot be used on the public internet. If a router that is on the public internet sees a packet with destination address one of those, it will drop it. It will say, I don't know what to do with it, probably. As a convention, usually, if you mean, I don't know which address, you put zeros everywhere. This is useful sometimes when you have a protocol or a software that has a field for an address, but you don't have a value, then 0 means always absence of address, which means it's also an invalid address. There is no IP address that has 0 everywhere. No, nobody has this address. You have also one address, in fact a group of addresses, but in practice most of the time only this one is used, which is called the loopback address, which means this host. So if you send a packet to this destination address or to any destination address in this block, it will stay in the machine. It will stay there. Why would that be useful? Yes? To communicate with a web server that's on your own machine, exactly. For debugging in general, if you are writing programs that are supposed to run on a client and a server, then it's much more convenient, and you will be able to experience that in Lab 3, to first do it on your own machine before trying on the network, because on your machine everything will be simpler. And if it doesn't work on the network, it may be because of your program, or because of the network, or because of the address, or whatever. So that's very often used as a debugging tool. Also as a way to bypass some configuration problems. If you want to talk to a process that is normally done by some software that you have no control on it, but you'd like to communicate with it, then you can communicate by using those addresses. So it's a way to do what is called also inter-process communication. TCP and UDP provide you a way for two processes to communicate, in principle over a network, but you can do it also over the same machine. And the interest is that if you think that your processes might be distributed on different machines, then you can do it from the start using those loopback addresses. When you will distribute them, you don't have to change your programming functions, but only addresses. Then there are other kinds of private addresses. Those ones are called link local, 169.254. Link local, that's a terminology that means same LAN. Link local, on link is another terminology. Two systems are said to be on the same link if they're in the same local area network. For some reason, link means local area network here. And those linked local addresses means they can be used only for systems that are really completely isolated. For example, you go to a desert island where you have a computer and a printer, and you want to print a map of something or to leave a message for somebody who will come and rescue you. So you need to have your printer to talk to or your computer to talk to your printer. So you need two addresses if you use TCP-IP, which probably you do. And then one way is to use those addresses. So this is typically done by Windows machines, for example, when they boot and they find no information. You have not configured an IP address like we do in the lab. There is no configuration server, DHCP server. We'll come to that in a few more minutes. So they have really no address and they need one. So they will randomly pick one of the addresses in this block and will do an address duplication test, and therefore they will get addresses that will work. So your printer will have one of these addresses, your computer will have another one, and then they can talk to each other if they're able to discover who has this address. Then there are specific addresses that are used for multicast. We'll talk about them in a module devoted to multicast. Multicast addresses are something completely different from all the rest of IP. Multicast, an IP multicast address is the identification of a group or a channel. For example, if you distribute TV over a Swisscom network, that's typically for live TV, you use multicast, and every channel used by Swisscom TV corresponds to one IP multicast address. They are very different from the normal IP addresses. Normal are called unicast address in the sense that they are completely logical. There is no meaning associated to there is no topology meaning associated to a multicast address. So when you see a multicast destination address, you have no clue where the destination is. So we'll see how this is handled. This is reserved in case somebody has a need. That's a very short block. And this, which you recognize as a string of 32 bits equal to 1, the all 1 means broadcast, right? Link local broadcast. Of course, the only broadcast you can do in the internet is on a local area network. Local area networks accept to have broadcast. The internet does not. You cannot send a packet to everybody in the world, of course. This is the IP packet header that you have started to observe in the packet capture traces. The main thing that we have in the IP packet header is the destination address. We've seen that we need also a source address for the destination to respond. The source address is also used by routers in practice. Although the theory I said says the routers look only at destination address and they do longest prefix match, but in practice they also look at the source address. Why that? Can you imagine a reason for that? Yes?
Maybe for security.
For security, can you expand on that?
IP spoofing.
What is IP spoofing?
When you put another IP source as a root.
Exactly. IP spoofing is somebody that the bad guys does, pretending that you are the IP address of someone else. So you send from somewhere that's not at EPFL an IP packet with source address EPFL. If routers look only at destination address, that will work. And that's a way to do lots of attacks. You can, because if I send to a server, if I have robots, for example, malware robots that are distributed in the world, I have 1 million of them, and they send to lots of machines packets with the source address of my machine, then I will receive responses from all over the world to me. So that's a very easy way to do a denial of service attack. And other attacks, as you can imagine. So in practice today, on the global internet, the routers do what is called reverse forwarding check. So they check that the source address that you receive comes from the direction to which that makes sense, which is a possible direction to which you send a packet. So if you are, for example, outside EPFL and you receive a packet that comes from Zurich, you say, well, it's not okay. An EPFL packet should not come from Zurich, it should come from Lausanne, so you will drop it. You can access the EPFL network in Zurich with VPN, but as we will see, that's another story, and the source IP address would not be an EPFL address visible by Swisscom, for example. Then there's a number of other fields. Some of the fields here are used for fragmentation that we'll discuss later. An important field is called the protocol in IPv4. Protocol here means the type of the nature of what's inside the IP packet, typically UDP or TCP. Those are the most frequent protocols that we will see here. Then there's a number of flags that we'll discuss a bit later that are not really useful. The version is always 4, so that's one of the problems, I believe, of the internet. So an IPv6 packet is not the same with number 6 here. An IPv4 packet is always this and always 4. The packet header also contains the total length, which is the length of the header plus the payloads, which may be redundant with the MAC layer information, but is often useful. Yes?
Why do we put the protocol what's in the payload in the IP headers? Wouldn't it be in the header of the transport?
So why is the protocol here and not there?
Yeah, not in the...
There's a good reason. Can you find out? Well, all of this, I mean, I say protocol here, but all of this is just zeros and ones, right? If I send a packet to you or to the PCAP software, the Wireshark software that displays the packet, I mean, how does Wireshark know it's a TCP packet? By looking at the TCP packet, you cannot know it is a TCP packet because a TCP packet is nothing else than a sequence of zeros and ones or a sequence of bytes, right? If someone tells you it is a TCP packet, you can analyze each of the fields in the TCP, you can analyze each of the bytes and make sense out of them. But if nobody tells you it is a TCP packet, it might as well be a UDP packet or some kind of new stuff that you've never seen before. So the only way to know it's a TCP, not the only way, but the only practical way to know it's a TCP packet is that another layer, in fact the layer below, tells you it is a TCP packet. Yes?
But there is a transport layer header.
Yes, there is a header here. Yeah.
Okay, so it's not standard, it's not the same for different protocols?
Of course, the TCP transport layer header is the business of TCP. The UDP transport layer header is a different thing. And if you invent a new transport protocol, you invent your own header. If you invent a new application layer protocol, when HTTP was invented, they defined their fields in their own way. Otherwise, that would have meant that somebody had the global design and had to invent all the fields of all the protocols that will exist in the future. That doesn't work. We can ask the same question, how do we know it's an IP packet? Yes?
Because there is the same field in the MAC header.
Exactly. In the MAC header, there must be the same field. And the MAC layer, how do we know an Ethernet packet is an Ethernet packet? Well, the answer is because it's received on an Ethernet adapter, and the only thing that an Ethernet adapter can do is to receive an Ethernet packet. Voila, we do a break, and we will continue this exploration in 15 minutes.